The roller coaster problem is a classic example. I have seen it in every textbook from introductory physics. Let's say we have a 12,000 kilogram roller coaster that is moving at 20 meters per second when it is 10 meters above the ground. The question here is how fast will it be moving when it reaches the next hill 20 meters above the ground? Since this is a question of energy, and the questions of roller coasters moving along the various tracks are invariably 99% of the cases always solved through some conservation of energy principle, let me choose here ground. A natural choice will be the bottom of the track. Remember, we need to set up a ground if we work with the potential energy. The potential energy formula always requires us to have a reference frame. With that ground chosen at the bottom of the track, the roller coaster starts 10 meters, so this will be the height of the hill A. The height of hill B will be 20 meters above the ground. Now I'm ready to write down the energy. The total mechanical energy of the roller coaster while it's on the hill A will be the sum of the kinetic and the potential, or 1/2 of the mass of the roller coaster times the velocity of the roller coaster squared at that hill A, plus the potential energy, which will be the mass g, which is the gravitational acceleration, times the height. In this case will be 10 meters. Now let's see what happens on the hill B. When the roller coaster reaches the hill B, the total mechanical energy again will be the sum of the kinetic and the potential, or 1/2 m, the mass of the roller coaster, times the velocity now at the hill B squared, plus the potential energy, which is the mass, the gravitational acceleration, and the height hb. We're going to apply the conservation of energy principle, which sets up the mechanical energy at hill A to be equal to the mechanical energy at hill B. In other words, we're going to have 1/2 of mva squared plus mgha. That was the mechanical energy of the roller coaster while it's at the hill A, has to be equal to 1/2 of mvb squared plus mghb. Something fun happens here. We can actually cancel mass, and you can see why many of the problems in your physics textbooks actually will omit the mass of the roller coaster. So if you ever solve a problem of an object rolling down a hill without the mass, it's okay. You can still solve the problem. Just work out with the symbols and you'll see that the mass will cancel. Let me write the simplified equation here. After we cancel the masses, we're going to have 1/2 the velocity or the speed of the roller coaster at the hill A squared plus g times the height of that hill A. Has to be equal to 1/2 of vb squared plus g times the height of hill B. And here's where I plug the numbers. Now the given numbers from the problem, I know the velocity on the hill A, which is 20. I also know the height, so the first two terms are going to be 1/2, 20 squared, the plus 9.8, that's the gravitational acceleration, times 10. This has to be equal to 1/2 of the velocity of the roller coaster when it reaches the hill B squared, that is the unknown of this question, plus 9.8 times 20 meters, that's the height of hill B. The first two terms turn out to be 298. I'm going to copy the 1/2 of vb squared, because the v is here the unknown, plus 196 from the last term, which eventually gives me for the velocity of the roller coaster once it reaches hill B, the top of hill B, to be 14.3 meters per second.